Hi everyone, I'm Mrs. Erickson, one of the fourth grade teachers at Marquette Elementary School. Today we're going to go over a problem string. You might remember problem strings from third grade, but if you don't, problem strings are a series of connected problems that we solve one at a time. Oftentimes we start off with an easier problem and it gets harder as the problem strings continue. The problems at the beginning of the string often help you solve the problems toward the end, and our goal is to think like a mathematician and find the most efficient way to solve these problems as we move along the problem string. The first problem that we're going to solve in the problem string is 5 times 8. And for this problem string, we're going to use area models. So as a reminder, I put the vocabulary card for the word area down here. So area is the total number of square units needed to cover a two-dimensional surface. So you can see right here, we have a picture of an area model. So if we're drawing an area model to think about 5 times 8, we can also think about it as we're building a garden. Let's say we're building a garden and one side of the garden is going to be 5 feet long and the other side is going to be 8 feet long. How much total area will the garden take up after it is built? This is what an area model for the problem 5 times 8 would look like. 5 is on one side, 8 is on the other, and the answer is in the middle. So a 5 by 8 garden would take 40 square feet. The next problem in the problem string we're going to solve is 10 times 8. So remember, with problem strings, we start with an easier one and we build up to harder ones. So think about how you can use the area model in the first problem, this 5 by 8 area model, to solve 10 times 8. You might have noticed when we solve 5 times 8 and then solve 10 times 8, only one of the numbers is changing. 5 is doubling to become 10. That means that our area model needs to double as well to solve the problem. Here you can see how the 5 by 8 area model has been doubled to create a 10 by 8 area model. The 8 side of the area model did not change because the 8 didn't change in the problem. But 5 plus 5 is 10, so when you double this, you now have a 10 by 8. And we know the answer to each of these, the 5 by 8 area models is 40. So when we combine those two answers to get an answer to 10 times 8, it equals 80. So let's try it again. Let's double another number in this problem. So now let's try 10 times 16. Notice here, the 10 stayed the same from the last one, but the 8 doubled to become 16. So think about how you can use this area model right here, this 10 by 8 area model, which gives us an area of 80, to solve 10 times 16. So when we moved from 10 times 8 to 10 times 16, the 8 has now doubled. Okay, so we're going to double our area model again. So when we look back, this is what we solved in the last problem, 10 times 8, right? We can also think about it like this. These two models represent the same problem. This is just breaking down that 10 down in half. Now over here, what's happening is they doubled this model, so now we have 16, right? If you split it in half, there would be 8 over here and 8 over here. So when we split it up like this, we can also see that there's 80 here and 80 here, and this would give us a total of 160. So all I did was double this, right? So it became 10 times 16, and then we doubled 80, so 80 plus 80 equals 160. So let's review what was happening in those three problems. We started with 5 times 8. And we moved to 10 times 8. The 5 doubled, right? And then we moved from 10 times 8 to 10 times 16, and in that, the 8 doubled. Now, let's think about what's happening to the product. So as a reminder, I'll move my camera. The product is the answer to a multiplication problem. It's what you would find in the middle of those area models. And then a factor are the numbers that you multiply together to get the answer. Okay, so for example, in 5 times 8, 5 and 8 in factors, and then 40 is the product. So what we're noticing here is when one of the factors doubles, so when 5 doubles just one of the factors, the answer doubles, right? So this was 5 times 8 equals 40. 10 times 8 equals 80. The answer, which went from 40 to 80, doubled, as did one of the factors. So when you double one of the factors, the answer also doubles. And the same thing worked when we went from 10 times 8 to 10 times 16. The answer to 10 times 8 is 80, and the answer to 10 times 16 is 160. So what was happening is the answer is doubling along with one of the factors in the problem. This is an important pattern to notice because you started with a simple equation like 5 times 8, and you were able to use that to work your way up to a problem like 10 times 16, which is a little bit more complicated. So now let's think about what happens when the opposite happens. We know when we double one of the factors, the answer doubles. But what if we cut one of the factors in half? So now what we're going to do is we're going to think about this equation right here, 5 times 16. So remember the last one we solved was 10 times 16. So all that's happening here is we're cutting that 10 in half. So what do you think is going to happen to the answer or the product? The answer will also get cut in half. So the same type of thing happens. If the factor doubles, the product doubles. If the factor is halved, the product, the answer, is also cut in half. So when we think about this problem 5 times 16, I'm actually going to go back and look at 10 times 16. And I'm going to cut this 10 in half. Okay, so when I cut it in half, what I'm left with is 5 times 16. And we know that half of 160 is 80. So I can now use that problem before to solve this problem. So as a reminder, the big idea to keep in mind is that when you double one of the factors, the answer also doubles. And if you half one of your factors, the answer is also cut in half. Now remember, we're talking about multiplication problems. So you are going to try a different problem string on your own. Come back and rewatch the video if you need any help. Good luck!